or maybe like that. Okay, so let me start now. Okay, so thank you everyone. A very good afternoon to all of you. This is the week 4 of this NPTEL lecture series of soil mechanics geotechnical engineering 1, in which we are studying the various aspects of the soil mechanics with the basic concepts. Starting with the origin of soil, we have read the permeability and many more things in the previous 3 classes. We also solved some problems, and I think so in the meanwhile you come across the assignments problem as well. Okay, so first of all, my name is Sumit Kumar. I am the PhD research scholar at IIT Islamabad. This course is taught by Dilip Kumar Vaid sir. So I am taking this session in which I try to cover the problems specifically so that it will be helpful for you while going ahead. In brief, we also discuss the concepts which has been covered during this week. In addition to that, the content of this lecture will also be shared with you by the NPTEL team. These videos are lectures are recorded. Those who are not able to connect me in the live class can able to see these videos through the YouTube link which will be shared with you. Apart from that, the whatever the content PDF presentation or anything which I am showing over here is also shared with you by the NPTEL team. Uh, Google Drive link is already shared with you so that you can see the contents over there. In addition to that, the assignment is also need to be submitted by all of you in order to get the marks before the final examination, which will be complied at the completion of this course. So these are the basic instruction. In addition to that, I want to add that due to any problem, network error, if my call get disconnected, please be remain in the meeting. I will rejoin and start from there only. And this is not frequent thing that will happen, but as today you have seen that I have connected at 3 only, but due to some system error, I could not able to communicate with you. So this type of problem may arise sometimes. So please be patient. Okay, thank you everyone. So now I will start with the content. So this is the soil mechanics class. In this lecture, we are studying about the concepts of stress, effective stress, total stress, and compaction. To a brief, and today class is covered with the many problems, many numerical problems which are quite useful for you for developing the understanding of the subject. So first of all, a brief theory which is discussed in this previous sessions I will cover, but that is not the main focus of my today class. The main focus is the numerical problems, and at the end some multiple choice questions which I always give in the every class. Whatever the PDF I have shared with you, some multiple choice question were there. So I will suggest that you will solve those problems, and some of the other numerical problems from some standard soil mechanics book, whatever book is available with you, if you will able to solve it, that will be very much helpful for the better understanding of the subject, right? Okay, so the over here starting with the brief theory, then we move to the numerical problems, and numerical problems is basically based on the effective stress, total stress, and port water pressure. Okay, so over there, if in the theoretical concept is not discussed, I will discuss those concepts before moving to those problems. But let's see. Starting with the compaction of soil. So over here, the dynamic densification is a word in which the dynamic compaction is used on an unsaturated granular geomaterial, and the impact of the heavy temper immediately displaces the particle to the denser state and compresses or expels the air out of the void and reduces the volume of void. Okay, so first of all, in the previous class, if you remember, we have read about compaction in a very brief. Over there we talk about optimum moisture content, maximum dry density. If you remember, we have created a plot in which the water content is there over here and the gamma d is on the y-axis. If you have remembered the previous class and if you have solved the problem and if you have seen that some this type of graph is there in which the water content is on the x-axis and the dry density is on the y-axis, and we have seen that if we increase the compaction effort, its maximum dry density value seems to be increasing while the moisture content each seems to be decreasing. In this fashion, we are able to find the OMC. So that compaction basically replaces the void, reduces the void, and result in the densification of soil. That is the main factor which we want to achieve over there. And in any construction process, if you have seen some of the road construction or maybe the railway construction, over there you see that the soil is compacted with a different type of rollers and some type of pneumatic rollers and different type of rollers we also have came across in the previous class as well. Over there you have seen that the water tank is also there in which we water flow out. Afterward we roll it to achieve a specific moisture content and the density in order to densify the soil over there so that we can construct the super structure over there. Maybe that's the highway. In addition to that, if we are constructing any roadway, railway, or maybe as you know in the second lecture we have read that the the consolidation, the one dimension consolidation, two dimensional consolidation, three dimensional consolidation. So that takes the large time to small time depending upon the type of soil. Suppose if we have a sandy soil, over there the compaction takes place during the construction process only, but if the clay soil is there, it will the overall compaction takes place maybe 100 years, 200 years. So that things need to be understood. Hence we want to densify the soil as much as possible before any construction of the superstructure. That is also valid for the building construction as well, right? Okay, so I will go quickly with that this and then move to the problem. So over here some points is there, like the deep dynamic compaction is generally not recommended for the clay soil with the high plasticity index and the high degree of saturation. The drainage and the dewatering are required to reduce the excess water pressure in the clay soil generated by the deep dynamic compaction. Okay, and a high water table reduces the effectiveness of the dynamic compaction, right? If the water table is high and there is a dynamic compaction is performed, in that case the effectiveness gets reduced. The where the application of dynamic compaction is there, so it is used to improve the problematic geomaterial by increasing the bearing capacity, reducing the settlement, minimizing the collapsible potential, and mitigating the liquefaction potential for the commercial and residential buildings, storage tanks, highway, railway, airports, harbors. Okay, now talking about the advantage. What are the advantage? What are the benefits which we achieve through the compaction of soil? So it improves the large area of geomaterial in a relatively shorter time at low cost, and the effectiveness of the loose and partially saturated fill with less than 50% fine can detect weak or loose area during the operation and can change the heterogeneous material to more uniform. And that is very much important, because if we denser and the strong material, and as it is mentioned earlier in this in the previous class as well, that over there we have talked about the gradation of soil. We have named the gap graded, well graded, poorly graded. on the basis of that we have classified the soil as well as per the Indian soil classification system. So we want to achieve the soil which is a well graded soil in which the odd size of particles is there. As you remember in the previous class, I have given some examples of a tank in which we kept the large size particles in which the different voids are there. In the other case, we have kept the large size, small size, and different size particles so that the all size are all size of particles are present. Hence, it is well confined, and hence that is said to be the well graded in one way or the other. So that example which we have discussed, so that condition we could achieve through compaction of soil. Okay, so the major equipment needed for this method is a crane and a temper, which are readily available, as also shown in the previous slide figure. Now, moving to the disadvantages of the compaction of soil. So, generally, less to not effective to improve the saturated clay soil. It is already said that if the water table is there, it is a problem. So this in saturated, the water table is present up to the ground level if it is fully saturated. Okay, let me explain one thing. I think so that thing is not discussed yet. So let me explain you one thing before moving ahead. Okay, let me read this disadvantages. Then I will. I want to discuss some important point which is very much important for this class. So let me read the disadvantages. Then I discuss some points. Okay, so uh, drainage and the dewatering and a long waiting period is required to use the saturated clay soils, and it induces noise, vibration, and the lateral movement, which may cause problems to the nearby buildings, substructure, and utility lines, maybe like the pipelines which move from over there, and the mobilization cost may be higher when the large crane and tempers are used. Required instrumentations to monitor the various aspects. Okay, so I want to discuss something. What is this, that? Let me add a blank slide. Okay, see, suppose this is a soil. Okay, over here a soil is there. So if there is a no water, if in this soil, this is a ground surface, right? So the we have read about the various type of dry density like gamma dry, yeah, gamma saturated, gamma bulk. We have understood, we have read the formula as well. If you remember, if you not remember, that's not the problem. Okay, I will write the formula for you as well. Gamma dry is G into gamma W, where G is the specific gravity of soil, gamma W is wet density of soil, and 1 plus E. E is the void ratio. Void ratio is the volume of void by volume of solid. Similarly, gamma sat is, okay, that is equal to, I think so, that is understandable. So this is G plus E upon 1 plus E into gamma W, where gamma bulk is G plus SE by 1 plus E into gamma W. Okay. Over here, G is the specific gravity, E is the void ratio, S is the degree of saturation, and gamma W is the density of water, wet density of water, basically. So over here, what I am saying that this is the soil, and may consider that water table is present at this level. Okay, and we could assume that water table over here, the soil is dry. above the water table, dry. Maybe bulk density could also be there if due to some seepage, negative pore water pressure develop, or maybe some other condition. If water gets soil gets saturated over here, the gamma saturated could be there, but if it is not mentioned anywhere in the problem, it is gamma dry. Okay, and over here the gamma saturated is there. Okay, and now some more important point which you need to understand before moving ahead, that if gamma saturated is known and gamma dry is known, now understand that what is the total stress and what is the pore water pressure and what is the effective stress. So three term is very much important. One is total stress, total stress. So total stress is written as sigma. Okay, and then pore water pressure. Pore water pressure. Okay, I am writing from mouse, so this is little bit difficult for me. So some spelling mistake or anything is there. Please understand by yourself what I am saying. That this is represented by U, and then effective stress. Effective stress is effective stress. Effective stress is represented as sigma dash. Okay, and this sigma dash is sigma means total stress minus pore water pressure. Okay, I think so. Up to this understanding is very much clear. Now let me take another slide to explain some more point about the total stress, pore water pressure, and effective stress. So what is this? Let me take a new slide. Okay. Now see. Suppose I give a simple example. Again with the same figure. Suppose this is a soil, and suppose at this point this is a distance of 2 meter, and this is also 2 meter, and we want to get the total stress, effective stress at this point A. Okay. At this point we want to get the total stress, effective stress, and pore water pressure, and suppose water table is somewhat over here, and this is a ground surface. Okay, so ground surface is represented like this. Water table is represented by inverted triangle, so water table is there, and the unit weight for this uh, gamma, suppose 16 kilonewton per meter cube. Okay, and gamma for this may be 90 kilonewton per meter. Okay, okay, 19 kilonewton per meter. And in this case, assume gamma WH gamma W means gamma W as 9.81 it is, but assume as 10 just for understanding. Now, so if we have to calculate the total stress, pore water pressure, and effective stress at A, we write total stress as sigma. I already showed. So total stress become 16 kilonewton per meter cube multiplied by 2 plus 19 into 1. Basically, this A point is at 1 meter. This A point is at center of the second layer, 1 meter. Okay. Okay. So you write 1 into 19. So this becomes 16 into 2, 32, 32 plus 19, 42, 51. 51 kilonewton per meter square. I will not write unit, you understand by yourself. Okay, right. Kilonewton per meter square. Right. So this is the value of total stress, because the total stress, pore water pressure, and effective stress came many times in this class. So I take a very small, simple example to explain it. Then we move ahead and see some more thing. Now, pore water pressure. Pore water pressure is the weight density of water into depth of water table. So water table is at this point. So this is 9.81 into 1, or if you have a assume 10, so it is 10 into 1. So 10 into 1 is nothing but 10 kilonewton per meter square. Now we calculate the sigma dash, that is the effective stress. So sigma dash become total stress, that is 51 kilonewton per meter square, minus pore water pressure, that is 10. That means that become 41 kilonewton per meter square. So this is the basic concept. Now you can make a triangle as well for the total stress, pore water pressure, and effective stress. For the total stress, you see the stress at this point. This is 1, this is 2, this is 3. At point 1, total stress is 16 into Z. So at Z, equal to 0, 16 Z equal to 0, hence this is 0. At 2 meter it becomes 16 into 2, 32, so it is 32. And at uh, as we move ahead, it become over here, this value is 32. Then the total stress move on, 19 into 2, 38. So 32 plus 38 become 40, 30, 70. This distance is 2, and this distance is also 2. If you find the area of this is the total stress triangle. Similarly, when you draw the pore water pressure, so pore water pressure at up to this point is 0, and from here downwards it becomes gamma W into Z. So gamma W is 10, 10 into Z, 10 into 20, this becomes 20 kilonewton per meter square. And when you calculate the pore water pressure, effective stress, you subtract this minus this. So up to this point there is no change, that is 32 only. From here onwards it become 9 into 2, 18, 18 plus 32, it become 50. So this is sigma dash, this is U, and this is sigma. Okay, so this is the very brief descriptions. I think so things are clear, but if still some doubts, there are many more problems coming ahead through which we can explain many more concepts. Okay, so give me a minute. Okay, okay, let me move ahead. Okay. Okay, so now we will talk about design consideration. So before the design of the deep compaction, a geotechnical investigation is required to evaluate the site condition, which include the geotechnical profiles. Okay, so different property at the site is also need to be understood, like the particle size, how much fine content is there, what is the degree of saturation, what is the Atterberg limits, because that become very much important before we ahead. As we have discussed some example of the total stress, effective stress, pore water pressure. Over there also we require the density of soil, so that is calculated only when we have the knowledge of the field characteristics. So the relative density of the cohesion ratio material groundwater level. If groundwater level is not known to us, we could not able to calculate the effective stress. Similarly, the void ratio and the degree of saturation is also some important parameter which need to be known in order to proceed with the discussion. Okay, now you see that the factor which influences the design of deep dynamic compaction should consider the factor of following influence, like the geomaterial type, depth and area of improvement, tempered geometry and weight, the drop height and energy, the pattern, spacing of drop, depth of cutter. So these are some things which need to be explored. Okay, so over here the US standard ships numbers is mentioned, so that is not the point of discussion at this point of time. Mm, we are very much okay. This is also one of the table which is talking about the degree of saturation for the different soil types. So that is not the thing which we going to discuss. These are the theoretical things. Now we directly move to the numerical problems uh, for saving the time. Okay, okay, now we come across the problems which I want to discuss in this class only, because these problems have very much importance in developing the understanding of the subject, because the theoretical concept you must go across the lecture of the sir. Over there they have discussed in very detail, but the numerical problems may be missed out. So it is better to cover the numerical problems. So over here you see that the question related to critical hydraulic gradient. I think so. The critical hydraulic gradient is something which we also calculated in the previous class. Over there, if you remember, we have calculated IC as critical hydraulic gradient as G minus. Okay, we have calculated as G minus 1 upon 1 plus E. Okay, as a critical hydraulic gradient. and IC by I equal to factor of safety. So those things we have discussed. But what is the problem over here? Let me read this first of all before moving to any of the concepts which we need to be covered for this problem. So questions say that a large size excavation is made in a stiff clay whose saturated unit weight is 17.27 kilonewton per meter cube. Okay, so gamma sat is given as 17.27 kilonewton per meter cube of the excavated field. When the depth of excavation reaches the 7.5 meter, crack appears and water begin to flow upward. Bring up sand to the surface. Subsequent boring indicate that the clay is underlain by the sand at a depth of 11 meter below the original ground surface. So what is the depth of water table outside the excavation below the original ground level? I think the similar type of problem which we have covered in the previous class as well. So let me read the problem again and discretize it separately. So first of all, it said that a large size excavation is made in a stiff clay whose saturated unit weight is 17.27. So there is a field from which the excavation is made. The saturated unit weight of that is 17.27 kilonewton per meter cube. Now, the second part of the question's problem statement say that when the depth of excavation reaches the 7.5 meter, crack appears and water begin to flow upward. When the excavation is made in that field up to the 7.5 meter depth, the water begin to flow in the upward direction, bring up the sand to the surface. So there is a problem. So subsequent boring at that surface only indicate that the clay is underlain by the sand at the depth of 11 meter below the original ground surface. From the ground surface, okay, let's see. From the ground surface, 11 meter below the ground surface, its sand layer boring indicate that the clay is underlain by the sand at a depth 11 meter. At the depth 11 meter, it is lain by sand and the origin to the origin from the original ground surface. And this is the original ground surface only. So, what is the depth of water table outside the excavation below the original ground level? So, I have already solved this problem. So, let's move to solution only. So, first of all, you say that the sand boils, so the effective vertical stress at the clay sand interface becomes 0, and the clay thickness below the excavation is 11 minus 7.5, because at the 7.5 meter excavation crack get developed. So the upward head difference over here is 7.5 minus dw, where dw is the outside water table below the ground below the ground. So the condition for boiling is effective stress should be 0, and effective stress is sigma v dash equal to gamma sat h minus pore water pressure, that is gamma w into delta h. So we have calculated the delta h as gamma sat upon gamma w into h, and gamma sat is already given as 17.27 and gamma W is 9.81 known to us, so delta H is found to be 6.16 meter. Hence, uh, um, we are interested in calculating the dw is the outside water table depth. So dw is delta h minus 7.5 oh sorry 7.5 minus delta h, so that is found to be 1.3 meter. So ground table outside the excavation is approximately 1.34 meter, or maybe 1.3 to 1.4 meter below the original ground surface. Okay, I think so this is a very simple thing. So now move to the next problem, which I will solve. Okay, over here also I have made the solution. Okay, but maybe I will solve with pen and paper, so that for the better understanding if it's required. Let me read the problem, because the previous problem, which the repetition of the problem which we have discussed in the last class, if you recall. Okay, so now see. Uh, Over here, the question say that if a excavation is carried out in a soil with the porosity 0.4 and the specific gravity 2.65, determine the critical gradient. Okay. Okay. So first of all, solve this part of the problem. If excavation is carried out with a porosity n equal to 0.4 and G equal to 2.65. Okay, so it says if the excavation is carried out in a soil with the porosity 0.4 and the specific gravity of 2.65, determine the critical gradient. So this much question is enough to solve the first part of the problem. So first of all, we need to calculate the void ratio in order to calculate the critical hydraulic gradient. E is nothing but n upon 1 minus n. If you remember, this thing need to be remembered by you. E equal to n upon 1 minus n, hence it is 0.4 by 1 minus 0.4, that is 0.6. So it becomes 2 by 3. Now, critical hydraulic gradient IC is G minus 1 by 1 plus E, if you remember. I have written in this class also and previous class also. So G minus 1 by G minus 1 by 1 plus E. So what is this? 2.65 minus 1 upon 1 by 1 plus 2 by 3. So let's calculate this. So this becomes 2.65 minus 1 upon 1 plus 2 by 3. So this is 0.99. This becomes 0.99. So it is at the verge of failure. Okay, so this value is 0.99. Now, the next part of the problem asks that a 1.5 meter of soil is subjected to the upward seepage head of 1.95 meter. So, what depth of course set would be required above the soil to provide the factor of safety of 2.5? If I remember, this same problem we have solved in the previous class. I didn't recall at this point of time, but it should look like the same problem which we have solved in the previous class as well. So I think so the understanding is very much clear for this problem, but let me solve this again. That the question say a 1.5 meter layer of soil is subjected to upward seepage head of 1.95 meters. So what is the depth of um, coarse sand would be required above the soil to provide the factor of safety of 2.5? Okay, so if you remember, we have IC upon I equal to factor of safety. Okay, so this factor of safety is 2.5. So I is equal to 2.5 into 0.99, and that is equal to uh, 1.5 meter layer of soil is subjected to upward seepage head of 1.95 meter. What is the depth of coarse sand? Okay, so this IE delta H by L, upward seepage head of 1.95. So this is equal to delta H upon L, and this delta H is 1.95 by L. L is nothing but 1.5 plus the required height, 1.5 1.5 plus H. So by solving this, you could able to calculate H, which is the required height. So this H become as let me calculate 2.59995 upon answer 5. Okay, maybe I made some calculation mistake. Let me see, this value going to become as 3.42 meter. I equal to seepage head 1.95 by 1.5. Okay, I have considered something different. 1.25, 1.5, 1.95 upon 1.5. Actual hydraulic gradient is 1.95 upon 1.5. So I is 1.3, but required factor of safety is 2.5. Okay, I have did this only 0.3999 upon this, and this much thing I have did, but what is the mistake I don't found? Delta H 1.95 by 2.5 into 0.65. Okay, so I made some mistake, calculation mistake, but over here they say follow same concept, and solution is came out to be 3.42 meter with the same concept. I have did factor of safety equal to IC by I required. So I required is found to be 0.99 upon 2.5 only. IC by I equal to I required equal to factor of safety. Okay, IC by factor of safety. I have the mistake over here only. IC by 2.5. So IC 0.29. Okay, okay. I don't know that how I've written this. This IC I equal to IC 0.99 upon 2.5. Okay. Now when you calculate, now let me calculate also, because this also give me confusion. 2.5, 1.95 upon answer. Okay, minus 1.5. So it's come out to be 3.42 meter. 3.42 meter. Okay, so this is the answer. This is this much height is of soil is required in order to achieve the factor of safety of 2.5. This is the solution only, and the same thing they have did, and they also found to be 3.42 meter, which we have found. Okay, so I think so things are clear up to here. Now this is also a problem which is based on the light compaction test, but this solution I have provided over here, I am not going to discuss it over here. This will be shared with you, you cover it by yourself, because this is not that much conversion, so that I don't want to waste time in this problem. We'll move to the next problem from here and solve this problem. So over here I am going to take a small 5-minute break, and in this meantime I request you to read this problem and try to understand, then we move to the solution of this problem. Okay, so over here I am taking a small 5-minute break. Okay, so it is 4:05, so we will start from 4:10. A small 5-minute break will be there. In a meanwhile, the question is visible on the screen. Kindly read the problem and try to understand, then we move ahead. Okay, am I audible? Anyone can reply, am I audible?
Yes, sir, audible.
Okay, okay. Thank you. Okay, so let's restart from there where we have left. Okay, so there is a question saying that a 1200-meter long embankment of width 8 meter and of 0.7 meter width, 1200-meter long, 8 meter width, and 0.7 meter depth, maybe thickness. Compacted thickness is to be constructed in a part of roadway project. The construction specimen requires soil to be compacted to the moisture content of 19.6% to achieving the dry unit weight of 17 kilonewton per meter cube. Okay, so over here the moisture content which need to be achieved is 19.6%, and the dry density which need to be achieved is 17 kilonewton per meter cube. Now the question say soil is to be excavated and transported to the site from a borrow pit where the soil has the moisture content of 15% and the bulk unit weight of 17.25 kilonewton per meter cube. Okay, so bulk unit weight is known over here. Water content is known over here. So dry density could be calculated as gamma D equal to gamma B upon 1 plus W. So, and that could be useful. Okay, let me write one relation. I'm going to solve it with pen. I already solved because it is a long problem. If I go solve with the pen and paper like this, and so it will take entire time of the today class in this problem only, and I don't want to restrict up to that only. So I just explain the things which I already solved in next slide, so that it will would be helpful for you. Okay, so this is what I am saying, that gamma D equal to gamma B upon 1 plus W. Gamma D is the dry density, gamma B is the bulk density, which is known by 1 plus W, where W is the water content. Right. Okay. So the question say that the soil is to be excavated and transported to the site from a borrow pit where the soil has the moisture content of 15% and the bulk unit weight of 17.25 kilonewton per meter cube. While loading into the dump truck, the soil loses and its dry unit weight dropped to 14 kilonewton per meter cube. Okay, no problem. Obviously, when it is taken from the borrow pit and kept dumped in the truck, its value could be changed. Okay. So the first part of the problem says determine the volume of soil to be excavated from the borrow pit. Okay, and two important things which you need to understand, that the volume of solid and the weight of solid remain constant. That doesn't change. The volume of solid at the borrow pit, volume of the solid at the excavation sites, both remain constant. Same with the weight of solid as well, because when we talk about the solids, there will be no void, and if no void, it's all the weight of the solid mass only. Hence, and the weight and volume of the solid remain constant. That is also one of the important aspects which we are going to use in this problem. So the first thing is to calculate the volume of soil to be excavated from the borrow area. Second is say the number of trips of the truck between the borrow area and the construction site, assuming that each truck can carry 7.5 meter cube of loose soil. Okay, that's not the problem. That is easily calculated once the volume of soil is calculated. Third part of the problem is the volume of water in cubic meter to be added at the construction site to achieve the desired moisture content of 19.6%, if you have remember from the problem. And the fourth part of the problem asks the degree of saturation of soil at the construction site after compaction. So that also is calculated when the specific gravity need to be calculated, right? Next part of the problem asks the moisture content of the compacted soil if the saturated after construction due to rainfall. Okay, so this is the 5 things has been asked over here. So let's go solution one by one. First of all, the embankment length is given as 1200 meter. Following, the width and the thickness is 8 and 0.7 meter respectively. With the compacted dry unit weight is 17 kilonewton per meter cube and the moisture content at that is 19.6%. Now, borrow pit has the moisture content of 15% and the bulk density of 7.25 kilonewton per meter cube. In addition to that, the question also state that during loading into the truck, the dry unit weight drop to the 14 kilonewton per meter cube from the 17.25 upon 1 plus W. So first step maybe is the total volume of the embankment, the volume needed is 1200 long, 8 meter width into 0.7 meter thickness is 6720 meter cube. Now the first part of this problem say the volume of soil to be excavated from the borrow pit. So we need to know the same mass of the dry soil that be compacted embankment using the dry unit weight kilonewton per meter cube and the dry weight required. So this become VC already calculated. So gamma D into VC in situ borrow pit dry unit weight. So first of all, we calculate gamma D. As I have already said, gamma D is 17.25 upon 1 plus W, where W is the 15%, as seen from the third point over here. Okay, let me take a laser. Okay, as seen from this point, so we'll calculate the dry density as 15 kilonewton per meter cube. We multiply it with this volume of 6720. We calculate weight. Divided by 15, so we could able to calculate the in situ volume required, that is the 7616 meter cube, which is asked in the first part of the problem, that the volume of soil to be excavated from the borrow area. Next thing, ask the number of trips truck required from borrow if each truck carries 7.5 meter cube of loose soil. Okay, so see the volume required is this much, that is 7.7616 meter cube. Now each truck carry the 7 meter cube, but one additional point is also mentioned over there, that when it is dumped in the truck, the dry density get changed. Sorry. From 17 to 14, so the volume of loose soil which is dumped on the truck become 8160. In similar manner, 17 into 6720 upon 14. This is the 6720. This is the 6720, and so this volume become 8160 when it is divided by 7.5, because 7.5 meter cube is the capacity of each truck. This become 1088. Maybe some calculation mistake is anywhere, so you can check it by yourself, but more or less this is the correct answer. Next part of the problem say that volume of water to be added at the site to raise the moisture from 15% to 19.6%. So first of all, compute the dry mass of the soil in the compacted embankment. Convert, so we calculate gamma D into 1000 upon G, that is 17 into 1000 by 9.81. It is the 1733.52 kg per meter cube. Now we multiply it with the 6720, which is the volume of the volume required. So it become 1.1645 into 10 to the power 7 kg. Now water mass occupy at present is the 15%. So this is this much kg, and water content required is 0.196. So extra water required is 2.2824 into 10 to the power 6 minus 1.7647 into 10 to the power 6. So this become 5.38 into 10 to the power 5 kg, and when it converted into volume by dividing the 1000 kg per meter cube, it becomes 535.7 meter cube. Hence 736 meter cube of water is required to be added in order to achieve the moisture content of 19.6%, which is request moisture content as per the stated problem. Okay, now the next part of the problem asks the degree of saturation after the compaction at 19.6%. So for that I have already said that void ratio is calculated as 0.5292, considering a GSI 2.65. So once the void ratio is calculated, and the other relation, that is SE equal to WG, is there, the degree of saturation is found to be 98.15%. Next, the moisture content, if compacted soil becomes saturated after rainfall, then the degree of saturation become 1. And at that point of time, when we calculate the water content at a saturated condition, it is found to be 19.97%. Hence, this problem gets solved out, and I will suggest to go by yourself and solve by following these steps, and check whether the solution is same or not, because if some calculation mistake is there, there might be chances that some error is there in the value, but the steps are more or less same. Right, now we move to the effective stress concept, which I already discussed in the two of the slides in the very early of this class only. Okay, so see over here, you can see that we are talking about the effective stress in soil. So the concept of effective stress was introduced in 1923 only by the Carl Turjak, who is also known as a father of soil mechanics. So earlier we used to calculate the stress as a total stress only. There is no effective stress concept. But so what is the need that we need to calculate the effective stress? Total stress is not sufficient to define or explain the things. So there must be some need, some requirement to come across with the effective stress. So the principle applies earlier is the total stress, in which we calculated the total stress based on the saturated unit weight or maybe bulk unit weight. So the this principle applies only to the saturated soil and relate to the following three stresses: the total normal stress on a plane within the soil mass being the force per unit area transmitted in the normal direction across the plane, imagining the soil to be solid material. Second one is the pore water pressure. I have already discussed about the pore water pressure as well. Now we go ahead one by one with some problem associated with this, and better understanding is developed for this concepts. So the pore water pressure being the pressure of water filling the void space between the solid particles. So the effective normal stress on the plane representing the stress transmitted through the soil skeleton only. Okay, so these are the things which we already discussed also, but now understand this in this with this figure. Over here you see the principle can be demonstrated by the following physical model, which is over here. So consider a plane axis. You see the axis is visible. So the consider a plane axis in a fully saturated soil passing through the interparticle content only as shown in the figure. The wavy plane x-axis is really indistinguishable from a true plane on the mass scale due to the relative small size of individual soil particles. A normal force P applied over an area A may be resisted partly by the interparticular force and partly by the pressure in the pore water. The interparticle force are very random in both magnitude and direction throughout the soil mass. But at every point of contact on the wavy plane may be split into the components normal and tangential to the direction of true plane to which the x plane approximate, and the normal and tangential component are n and t respectively, and the effective normal stress interpreted as the sum of the all normal component divided by area as a summation of n by area from that figure, and the total normal stress is given by sigma equal to p by a, and subsequently if the point contact is assumed between the particles and the pore water pressure will act on the plane over the entire area A. Then for the equilibrium in the direction normal to x-axis, summation of n dash equal to u into A, or P by A equal to summation of n dash by A plus u, or sigma equal to sigma dash plus u, or sigma dash equal to sigma minus u, which is the which means that the effective stress is equal to total stress minus pore water pressure. Right. Now talk about the critical points to note on the effective stress. Some of the most important points which need to be underscored, underlined, and need to be highlighted while discussing this total stress, pore water pressure, and effective stress concepts. So the pore water pressure which acts equally in the every direction will act on the entire surface of any particle but is assumed not to change the volume of particles. Also, the pore water pressure does not cause particle to pressed together. The error involved involved in assuming the point contact between the particle is negligible in the soil, since the total contact are normally being between the 1 and 3% of the cross-sectional area A. The effective stress is a concept that is the summation of normal load through the contact point divided by the total area. Hence it does not represent the true contact stress between the two particles. The actual contact stress Na, which is much higher than that of the effective stress defined. Now, talking about the effective vertical stress due to self-weight, it becomes gamma sat into Z, in which we consider a soil mass having the horizontal surface with the water table at the surface level, and the total vertical stress, that is the total normal stress, and the horizontal plane at the depth Z is equal to the weight of all material, that is the solid plus water only, because the void filled with air has no weight. And similarly, the pore water pressure become the weight density of water multiplied by the depth at which it is present, and the pore water pressure at any depth will be the hydrostatic, since the void space between the solids particle is continuous, so the depth change. Hence, from the equation of the effective stress derived previously, sigma v dash become sigma v minus u, where it becomes gamma sat minus gamma w into z, that is the gamma dash into z is the effective stress if the water table is present up to that ground surface. If that not the case, the things maybe looks different. Okay. Okay, so now we have a next problem, which is a very good problem. Okay, so let me take another slide in which I am going to solve it. Okay, so let's read the question first. Question says a layer of saturated clay 4 meter thick is overlain by the sand 5 meter deep. The water table being 3 meter below the ground surface. The saturated unit weight of clay and sand are 19 and 20 kilonewton per meter cube respectively. Above the water table, the unit weight of sand is 17 kilonewton per meter cube. If the sand to a height 1 meter above the water table is saturated with the capillary water, how are the above stress affected? Okay. So let me draw this soil profile first of all. So a layer of saturated clay 4 meter thick is overlain by the sand 5 meter deep. So this is a clay layer. This is a sand layer. This is 4 meter and this is 5 meter. Okay. So this is a 5 meter and this is a 4 meter clay layer. If the water table is being at 3 meter below the ground surface, water table is somewhat here, 3 meter below the ground surface, 3 meter. Okay. The saturated unit weight of clay and sand are 19 and 20 kilonewton per meter cube respectively. So saturated unit weight of clay gamma sat clay is 19, gamma sat sand अगर है तो it is 20. Okay. Now above the water table, the unit weight of sand is 17. So yeah, over here this and over here gamma is 17. Okay, no problem. Now, if the sand to a height 1 meter above the water table is saturated with the capillary water, how are the above stress affected? Now, you see, we calculate the total stress, pore water pressure, or effective stress. Anything we can calculate. Suppose we are going to calculate the effective stress model. So for here we write gamma we write sigma dash equal to sigma dash equal to for 0 to 3 meter. For 0 to 3 meter, we write Okay. And so this graph looks like this. 17 3 yeah, 51. From here onwards, it become uh, 51 plus 28 minus 9.81 digit. So this is for Z 3 to 5. So this looks like this become at 5 meter. The value become 51 into 51 plus 20. 51 plus 20 into 2 minus 9.81 multiplied by 2 is 71.38. Is 17 into the 51, and over here it become 51. At z equal to 0, it is 51 only. At z equal to 2, over here z equal to 3, 51 plus 20 into 2 minus 9.81 into 2. That equal to 71.38. If calculation mistake is there, you need to rectify by yourself. Okay. So this much is there. Now when we move to this cross section, it become um, basically like directly we calculate the effective stress over here. Effective stress over here as uh, 17 into 3. Let me tell only, and you understood. Is this becomes 17 into 3 plus 20 minus 9.81 into 2 plus 19 minus 9.81 into 4. So let me calculate by myself. It is 17 multiplied by 3 plus 20 minus 9.81 multiplied by 2 plus 19 minus 9.81 multiplied by 4. So effective stress is 108.14. 108.14. Okay, so you can see in the same manner this is drawn as 108.14 or something like that. But the the next part of the problem say that about the water table uh, above the saturated unit weight of clay is 19 and itna this above the water table itna. If the sand to a height of 1 meter above the water table is saturated with the capillary water, how is the above stress affected? So if a capillary rise and the soil gets saturated above for the 1 meter above this surface, then in a similar fashion what we have calculated over here, the the equation remains same, but something get changes, like for that 1 meter uh, gamma sat is there, but the pore water pressure is not reduced, because due to capillary rise, if water table is affected, if soil gets saturated due to capillary rise, that is not converted into the pore water pressure. Hence, the effective stress value gets changed like this. Okay, and I think so. I think so. The solution is also provided over here in this form, but this is not highlighted over there. So what changes is made is presented over here, that for what thickness what changes is made. So I will give you with the solution, but I think so this understanding is very much clear for everyone. Okay, so when we talk about the effective stress concept, before moving to the next problem, the variation in the effective stress with the shift in the groundwater table. For the water table below the ground surface, a rise in water table causes a decrease in the effective stress, and a fall in the water table produces an increase in the effective stress. Obviously, as you see that the water table below the ground surface, uh, a rise in the water table causes the decrease in the effective stress. If water table get rise, then pore water pressure get increased, and pore water pressure get increased, then the effective stress get reduced. But if the water table fall down, the effective stress increase, because the pore water pressure get reduced. So the total stress minus pore water pressure is the effective stress, hence it gets increased. Similarly, for the water level above the ground surface, the fluctuation in the exposed water level does not alter the excessive stress like this. Um, you see, if this is a soil surface and water level is at this place, but if water table reach to some other section like over here, and ground surface is here only, so effective stress doesn't get altered by the change of water table above the ground surface, because if you remember, the effective stress is nothing but total stress minus pore water pressure, right? So if the effective stress is total stress minus pore water pressure, so irrespective of if the water table is already at the ground surface, the it effective stress is gamma dash multiplied by h. This is h. If water table reaches above, then this pore water pressure value get increased by that much amount, and that is also subtracted at the same time from the total stress. So this value remain constant. It is, doesn't get altered as mentioned in the this point, that the for the water level above the ground surface, or fluctuation in the exposed water level does not alter the excessive stress, and the effect of the shift in a ground surface will cause a change in the effective stress, of the magnitude equal to the change in the overburden pressure. Obviously. Now this discussion we already made, if you remember, with the help of a example, but in brief, let me discuss it over here. Like if you see, mm, we also made the total stress, water pressure, and the effective stress diagram. So over here you can see that this is a soil sample of thickness Z1, and Z2 is the water above it, and we have to calculate the effective stress at point 1. So over here the stress diagram is presented. Now at any depth Z, soil in a hydrostatic pressure, that is pore water pressure at any depth Z is, if you see this figure, let me take a highlighter. Measure. If you see this figure, you can observe that this Z2 is the height of water. So the pore water pressure at this point and at depth Z below the soil surface is Z plus Z2 into gamma W is the pore water pressure. And at any depth Z, total stress is Z2 plus Z into gamma W plus gamma saturated into jet gamma saturated. This is not gamma submerged because I am writing total stress. And when we write the effective stress, it becomes sigma z multiplied by uz. So sigma z minus uz. So z into gamma submerged, not gamma submerged, gamma saturated. Z into gamma saturated plus z2 into gamma w minus z plus z2 into gamma w. When we solve it, we come to as z into gamma dash gamma submerged is the value for the sigma dash z when it is fully water table is fully above, that is it is in the saturated condition. Now you see the other case. In other case, again, uh, in the previous case, the water table in the piezometer is at the same level as that of the sample. But over here, the flow takes place in the downward direction. Over here, you see that the gamma bulk is again Z1. Okay, every notation is not mentioned over here, but it is Z1 plus Z2 minus H is the pore water pressure at B. At pore water pressure at A is Z1 plus Z2 into gamma W, while the stress at A is Z1 plus Z2 into gamma W plus Z1 into gamma saturated. Okay, so I think so. This discussion is very much clear. Over here, the things are confusing. But if you have understood this much is sufficient with the conceptual clarity, because Z and H is not visible in the figure A and figure A of this slide, so little bit confusing things might be there, but when we go with the problem, you will easily understood. Okay, IC equal to G minus 1 by 1 plus E, we already read. We also solved the problem based on this. This is the critical hydraulic gradient, in which Gs is the specific gravity, E is the void ratio. Now move to the next problem. And this problem says that for a soil profile given below, determine the total effective stress at point A. What will be total neutral and effective stress at point A if the groundwater level raises to the ground surface? And will there be any change in the effective stress at point A if the water table raises 2 meters above the ground surface. So I think so. Last part of the problem answer will be G. No, there will be no change. But let me explain you step by step this problem. So first of all, we calculate the density for this and density over here. So for that, over here we can consider gamma as gamma dry, and over here we consider gamma as gamma saturated. So gamma dry is G into gamma W by 1 plus E. When you calculate this, this comes to be 2.7 into 9.81 by 1 plus 1, and when we calculate it, this value come to be 13.24. Okay, the unity 13.24 kilonewton per meter cube. And when you calculate gamma sat is G plus SE. Okay, SE is not known to you, no? SE equal to WG. So G to 1 plus G plus SE by 1 plus E. The gamma bulk, but gamma sat is G plus E upon 1 plus E into gamma W. And this value is going to be 9.81 multiplied by 2.7 plus 1 by 1 plus E, and gamma sat equal to 18.15. Okay, so this value is coming to be 18.15. So over here this gamma sat is going to be 18.15. Now it say that the calculate the total what will be the total neutral and effective stress at point A. So total stress is going to be total stress is sigma. So total stress is going to be at point A as gamma D into 2, that is 13.24 into 2, 13.24 multiplied by 2. Okay. 13.24 multiplied by 2 plus 18.15 into 2. Why 18.5? 18.15 multiplied by 2. Basically, we are calculating the total stress at point A. 18.15 into 2 plus 19.62 into 4. And when we calculate this comes out to be 141.26 kilonewton per meter square. Now we have to calculate the pore water pressure at A. Pore water pressure at A is 9.81 into 2 plus 9.81 into 4, that is 9.81 into 6, because if you see, water table is here, and over here to here the pore water pressure get developed. If we apply the piezometer at point A, the water table raise up to this level, so 9.81 into 6 will be the thing which we going to calculate as pore water pressure. So U is 9.81 into 6, that is going to be 58.86. And effective stress is sigma dash effective stress is equal to sigma minus u, and sigma minus u is 141 minus 141 minus 58, and this value comes to be 82.4. Hence, the effective stress at point A is come to be 82.4 kilonewton per meter square. Now, the next part of the problem will say that what will be the total neutral and effective stress at point A if the groundwater table raises to the ground surface. If water table raises to the ground surface, this means the water table reaches over here. If the water table reaches over here, hence the what will be the uh, change in the effective stress and total stress. So total stress get changed, and effective stress also get changed at point A. So let me calculate the total stress and effective stress and pore water pressure respectively for that case also. So I think so the time is running out. Let me complete very quickly. So for this case, total stress gets changed to 18.15 into 4. Total stress sigma equal to 18.15 into 4 plus 19.62 into 4. So this value, when I calculate it, come to be 18.15 into 4 plus 19.62 multiplied by 4. This comes to 151.08. 151.08, and pore water pressure comes in this case as 9.81 multiplied by 8. 9.81 multiplied by 8, that comes to be 78.48. 9.81 multiplied by 8, 78.48. And sigma dash equal to sigma minus u, that equal to 151.08 minus 78.48, and that comes to be 72.6. Okay, so this much is the problem. Now the last part of this problem said that will there be any change in the effective stress at point A? Water table raises above the water surface. See, if the water table raises from this point to this point, if water table is there, the pore water pressure, if water table raises to height h, so pore water pressure develop is gamma w into h, gamma w into h. And when we calculate the effective stress, the total stress increased by gamma w h, pore water pressure also develop gamma w h, and that gets subtracted. Is the effective stress doesn't change if water table raises above the surface at any height, irrespective of any height. Effective stress at point A doesn't get affected, right? So that much the thing. Now some more problems is also there. Okay, let me go quick and solve all of them. This problem say that water is flowing vertically up a 2-meter thick layer of sand. The head loss in the flow is 0.8 meter. Calculate the effective vertical stress at mid height of the sand layer if the saturated unit weight of sand is 19.5 kilonewton per meter cube. Okay, so one important relation for the effective stress is uh, if water flow in the upward direction is sigma dash, that is effective stress, equal to gamma dash, that is a submerged unit weight, gamma dash z minus I is the pore water pressure hydraulic gradient into Z. Z is the depth at which we need to calculate the effective stress into gamma W. So over here in this question, gamma set is given as 19.5. So gamma dash become 19.5 minus 9.81. And calculate the effective vertical stress at the mid height, at the mid height of the sand layer, and sand layer is 2-meter thick. Hence this need to be calculated at z of 1 minus iz gamma w. I is nothing but 0.8. 0.8 is the head loss at in the flow is 0.8 meters. So I is 0.8 head loss takes place in the overall 2-meter flow. So 0.8 by 2 multiplied by z is 1 and gamma w is 9.81. Okay, so when you calculate this value sigma dash, this value come to be 5.76. But in the same case, if the water flow in the downward direction, this minus sign get changes into this minus sign, get changes into plus sign, because this is the relation that sigma dash equal to gamma dash z plus minus iz gamma w. If the flow takes place in the downward direction, it is gamma dash z plus iz gamma w. If flow takes place in the upward direction, the condition get changed into gamma dash z minus iz gamma w, right? So this is the case. Okay, now the next problem say that the effective stress concept. Again, the problem is question is like in a deposit of the fine sand, the water table was 3 meters below the ground surface, but the sand up to height 1 meter above the water table was saturated by the capillary rise. The sand above this height can be considered as dry. For sand, GS equal to 2.65 and equal to 40%. Calculate the effective stress at depth 8 meter below the ground surface. So this is the same concept. Solution I already made. So this is the given data, and first of all we calculate the bulk density, dry density at those two surfaces. Then we calculated the saturated unit weight for the capillary rise zone, so that we can calculate the total stress and the effective stress. Then subsequently we calculate the total vertical stress at depth 8 meter as 148.32 kilonewton. Then we calculate the pore water pressure at the same depth. Then we subtracted the pore water pressure from the total stress, that is the 148.32 minus 49.05 as 99.27 kPa, and the total stress, pore water pressure and effective stress at those places is mentioned over here. So I think so these things are very much clear for this problem. There will be no doubt if you go across by yourself. So up to this things are there. So now we are at the end of the session, but as I already mentioned earlier that some MCQ question is made by me for this session. So let me conclude that before summing up the today's session. So move to the small question. Hardly take 5 minutes to complete. 25 question and 5 minutes is there. So what is the primary purpose of soil compaction? So options are increase soil permeability, increase soil strength, reduce settlement, increase soil porosity, decrease soil bearing capacity. From the option only, the increase soil strength and reduce settlement is the correct answer. So option number B. Right. Next question say which of the following method is commonly used for the compaction of the cohesive soils? So for the cohesive soil, whether the SIP foot roll in the previous class, there is a table in which these discussion are there. So correct answer is option A, that is the SIP foot roll. Next question state that the optimum moisture content corresponding to maximum dry density, minimum dry density, maximum soil porosity, maximum permeability. So I know that if you have gone across the previous class, it is the maximum dry density. Option A, right? Next question say when the soil is compacted at the moisture content lower than the optimum moisture, the dry density increases, decreases, remain constant, increases first, then decreases. So option B is correct, that when the soil is compacted at the moisture content lower than the optimum moisture content, the dry density decreases. Next problem say that which of the following affect the compaction of soil? So soil type, moisture content, compaction effort, they are all of the above. So compaction effort affect, moisture content also affect, soil type also affect. So option D is the correct answer. Next question say that a standard Proctor test is conducted at a compactive effort of, okay, so this is not discussed today, so that's not the problem. Answer A is the correct answer, 32.5 kg of blow and 12 blow per layer. Okay, next question say which compaction test uses a hammer of weight 4.89 kg dropped from 450 mm. Again, this is not discussed today, but option number A is the correct answer for this problem. In next question, it asks that in the modified Proctor test, the compaction effort is less than standard Proctor, same as standard Proctor, greater than standard Proctor, unrelated to standard Proctor. So it is greater than standard Proctor test. Option number C is the correct answer. Next question say the dry density in a soil compaction is defined as the weight of moisture per unit volume, weight of soil per unit volume of soil, weight of solid per unit volume of solid, or weight of wet soil per unit volume. So option number B, that is weight of solid per unit volume, is the correct answer. Next question state that which of the following soil type generally requires more compactive effort. So it is the option B, that is the fine grain soil. Next is the effect of compaction on permeability of soil is to increase permeability, decrease permeability, no effect on permeability. So decrease permeability is the correct answer, option number B. Next is the curve drawn between the dry density and the moisture content is called it's called the compaction curve, consolidation curve, permeability curve, or stress strain curve. Oh, sorry, the compaction curve option is A, compaction curve. Next is the next is that increasing the compactive effort in the field generally result in the higher dry density and lower moisture content. Lower moisture content needed for the maximum dry density. Option number C is correct. Or the phenomena that at the optimum moisture soil attains maximum dry density due to reduction in the air void, excess water lubrication, oversaturation, soil particle size increases. Option number A is the correct answer. Reduction in the air void, that's why that is achieved. Next is if the moisture content is increased beyond the optimum moisture content, the dry density increases, remain constant, decreases, or become zero. So decreases. Next is the relative compaction is defined as the ratio of dry density to the maximum dry density. So option number B is the correct answer for this problem. Next is pneumatic roller are mainly used for fine clay soil, unstable soils under wet condition, gravel and granular soil for the better compaction or the compaction of silty soil. Option number C is the correct answer. Next is which equipment is most suitable for the compaction of the cohesionless soil? So option C, that is the vibratory roller, is the correct answer for this problem. The maximum dry density obtained by the relative compaction is 1.62 upon 1.8. So this value come to be option number A, 90%. Next is which of factor is not directly related to the soil compaction? So the soil moisture content, soil color, soil gradation, compactive effort. So the soil color is the correct answer. Next is the effect of compaction on soil strength. Increases in the shear strength, decreases in shear strength, no effect, or decrease in cohesion but increases friction angle. So option A is correct, that increase in the shear strength. Next is the higher moisture content beyond the optimum, the more the soil behaves like a liquid. And the next is if the soil compaction curve shift to the right, it means the optimum moisture content increases. And the final problem is like the which of the following is correct about the modified Proctor test. So this is not discussed in the today class. So option A is the correct answer, uses higher compactive effort than the standard Proctor test. Okay, with this the today class comes to an end, and I think so this class will be helpful to some extent to all of you. Thank you everyone for joining. Now I will end the today's session. We will meet again in the next class. Till then, I suggest you to cover some problem from some standard book related to this, and solve all the assignment problem which will be associated with this will be provided to you in the due course of time. Thank you everyone for joining. We wish you a very happy weekend. Thank you everyone.